Okay, here's another tool that is used to lift, for instance, a block of ice. And we can reason out how this works. We are going to, lift this by the cable, and what's going to happen at this point? When this goes upward, then these members are going to pivot about that point, and this member here, EC and EB, will become more horizontal. As they become more horizontal, it's going to push points B and C outward from the center, and these 2 points serve as pivot points. As point C moves outward and point B moves outward, then point F will move inward and point G will move inward. And we are then grasping this block of ice or whatever, and we can lift it. Now notice the block, we've got some notches in here, so that serves, in other words, we're both getting a horizontal compression on this block, but we're also getting the ability to lift it up by having these notches in here. Okay, so that's the way this device works. And the question is, then what we want to do is we want to draw the final free body diagram for member FB, and that is this member right here. And to do this, first locate each 2-force member, and I'm just going to notice that FG is not a 2-force member because it has a weight. In other words, this is FG here, and what do we see? Well, we have forces at points F and G, X and Y, but we also have the 500 pounds here. So that is not a 2-force member because I have this 500 pounds in the middle. But if we look, so go ahead and try to solve this problem based on what I just said. So pause the video. Okay, well, let's look at it. What 2-force members do we have? Well, this is a 2-force member, that's a 2-force member, that's a 2-force member. This is a 2-force member. So those are our 2-force members. I can take a free body diagram of this portion, and notice we are going to assume that this is weightless, so the actual tool has 0 weight, and that means that when I lift this up with a cable, I'm lifting 500 pounds, and that, it becomes obvious this force here is going to be 500 pounds as we lift it. And so when I draw my free body diagram of BCEH, then I have 500 pounds acting upward, and then since these are both 2-force members, I have a force acting along the axis of that member. And I'm calling that one FCE, this one FBE. We can look at this free body diagram and take the sum of the forces in the X and Y direction. If I take the sum of the forces in the X direction equals 0, I have F minus FBE cosine 45 degrees for the X component here, plus FCE cosine 5 degrees for the x component there. And that equation tells me that FBE is equal to FCE. I can't solve it, but I can say that those two are equal. Then if I take the sum of the forces in the y direction equals 0, I've got the 500 and then FBE sine 45 plus FCE sine 45. So those are the vertical components. I know that FBE is equal to FCE, so I can replace it. And then I only have one unknown. And I solve for FCE, it's minus 354. And of course, that's the same as FBE. So when I draw the final free body diagram of this, I flip the arrows around and I have 354 compression, 354 compression. Then what does that tell me? Then I have, it points, again, it points toward the body. And when I draw the free body diagram of these pieces, they're also acting in compression toward point B, toward point C at 354 pounds. So 354 pounds. So in addition, I've got a two-force member in the middle here, which means that I have an FAD for this one, FAD for that one, going from point A to point D. And then, like we said, the block is not a two-force member, so I have both an X and Y component, X and Y component. Now, the total load that we're lifting is 500 pounds, and everything is symmetric, so I know that I'm going to have 250 in each side, so that's going to be 250 there and 250 there in the vertical direction. So I look at this, there are lots of ways to get that, but in this particular case, that's pretty obvious, so I'm just going to let it go. You can read that, but I could also have taken a free body diagram of this, and I would find out that it's 250 for each one. But okay, so I have this free body diagram. I'm interested in that side, and you can just note the way things line up here. Point B and point F are along a vertical line, and so I can take a point along that vertical line K and take the sum of the moments about K, and that leaves me with my X component of 354 cosine 45 degrees, and the GX here is the only unknown, so I have minus 354 cosine 45 times 2, and plus GX times 1.5. I get GX is equal to 333.8, and then I can take moments about point F to get FAD, and so I have FAD times 1.5, and the minus 354 cosine 45 times 3.5, which is that distance there. And I can get that FAD is 584 pounds. So my final free body diagram looks like that. Okay, now this problem looks more difficult than it actually is. It's pretty straightforward, but Let me describe it. There's a 200-pound man, and he is pulling with a force of 50 pounds. So he's pulling this cable with a force of 50 pounds. It says find the reaction at point F. So I want the reaction right there. And I give you a little hint here. Do this by first creating a free body diagram that includes A, B, C, and the man. So I'll let you take that hint and work this problem. So pause the video here and work this problem. Okay, so the free body diagram looks like this. We come in here, we make a cut at A, we make a cut at B, we make a cut through the cable there, a cut through the cable there, a cut through the cable there, and that's it. So notice I made a cut here, I made a cut here, I made a cut there, under there, and under there. So what do I get exactly? I mean, I could show you so I could do my copy and paste exactly along these lines. And what does it look like? Well, it looks like that. That's what you should get when you draw a free body diagram properly, and then you can see where you made cut there, cut there, cut there, cut there, cut there. The man weighs 200 pounds, so that's what you need to add forces wherever you made cuts and put on the 200 pounds. So that is the method that you use to get a free body diagram that, you know, is slightly complicated. That looks slightly complicated. It's not. So since I made a cut at A, I put in my AX and AY. And since I made a cut at B, I put in a BY. And since I made the cuts through the cables, well, we've been told that the force that's being pulled with is 50 pounds. That means the tension in the cable up here is 50 pounds, which means that the tension everywhere in this cable is 50 pounds. And so I have 50 pounds that way, 50 pounds that way, 50 pounds that way. So remember, we're pulling so that it's in tension. And tension is away from the body. I have the 200 pounds here, and AX and AY for that, BY for that. So now I can look at this free body diagram, and well, I want to figure out what the BY is. So I take moments about A. And you can all do this. I've got the 200 times 5. And the, well, this was BY times 7. Minus, because it's counterclockwise. And then I have all of these tensions here. So I'm taking moments about this point. You know, I have my lines of action. 1, 2, 3. And so I have to take that perpendicular distance, and the perpendicular distance is like that. So I end up with 50 times 4, 50 times 3, 50 times 2. For those 3, I solve for BY and I get 207.1. That means I have 207.1 going up on this beam member, and then that means what? I have 207.1 going down on this beam. So I have the 207.1 on the left, I have unknown reaction there, and then the unknown reaction here. So the free body diagram looks like that, and I take moments about point E to get rid of those. I solve for Fy. Fy is 155 pounds. And that's what we wanted. Okay, here's another one. And this is a little more nonsensical, but no matter. But I've got the pulley on this piece here with a 200-pound load coming off that pulley and going straight down. And the question is to find the reaction at point C. And it says start by taking a free body diagram of the pulley and finding the forces at point A, which we've done before, and then does the roller touch the top or the bottom? So I've deliberately showed a little bit of a space here so that we don't know whether it touches the top or the bottom. Okay, so I'll just tell you there are no two-force members here because that's really the only member, and that is not a two-force member we can see. So it's got, 1, 2, 3 locations where there are forces, so it's not a two-force member. So go ahead and do this one. Pause the video. Give it your best shot. Okay, so it says start with the pulley, and that's fair enough. We know that this is 45 degrees. That's 200 pounds. So we know the tension in the cable is 200 pounds. And so I've got the 200 pounds acting at 45 degrees downward to the right, straight down 200 pounds. So, and then of course at the axle of this pulley, we have an AY and AX. So I'm looking at this free body diagram. I take the sum of the forces in the y direction equals 0, and that means I've got the AY going up, I've got the 200 going down, that's those, and then I have this 200, which of course I've got the angle 45, so it's going to be sine 45 because we're looking at the y direction, so it's going to be 200 minus 200 sine 45. I can solve that. I get AY is 341. And then I look at this also, and I take the sum of the forces in the x direction. So that's going to be 200 cosine 45 degrees plus the AX. AX plus 200 cosine 45 degrees. AX is negative 141 pounds. So that means that I have to flip the arrow direction. Looks like that. I'm sorry, if I said 341, I meant 141 for the X, 341 for the Y. Put that in there. So I have this, and, well, so what do I have? I've got 141 horizontal, 341 vertical. Again, it goes up. This one goes up. On this free body diagram, it goes also to the left on this free body diagram. I have to do the opposite of those for the adjacent free body diagram. Let's say the other free body diagram, which would be what? The L-shaped member, free body diagram for the L-shaped member. So that means that I have these forces, again, like I say, they're opposite, so I got the 341 going down, the 141 going to the right, and I don't know what the reaction here is, Bx, By, but I also have the Cy for the roller there. So I look at this free body diagram. I can take the sum of the moments about B equals 0, and you can see that we're going to get what? That's going to be a positive 141 times 40 inches. And the CY, sticking with the picture, is minus. So minus CY times 20. So 141 times 40 minus CY times 20. And we can get CY. Take the sum of the forces in the Y direction. So I have the BY minus 341 plus the CY. So I'm going to have BY plus the CY minus the 341. And we've already figured out what the CY is. So it's 282. Plug that in there. And then I could solve for BY, and I get 59 pounds. So, and then for the X direction, I do it in the X direction. And I get BX is going to be, you can see that, is going to be negative 141 pounds. So, my final free body diagram looks like this. So I have my X and Y coordinates, not coordinates, loads, and then I put those on there. Now I have my CY here. It came out positive, right? I showed it like this. It came out positive, so it's 282 pounds. Now what does that mean? I want to know, does it touch the top or the bottom? Well, remember that this load says what the support does to this wheel. Well, this says that the support pushes upward on the wheel. Well, it can only push upward on the wheel if it's touching the wheel. So, if it's touching the wheel there. So, we can go back and look at the actual, it's got to be touching here to be able to have a reaction that pushes upward. So for this particular one, we find that it touches at the bottom. It touches at the bottom. Remember, the free body diagram shows what the support does to the structure. And it says that the support pushes up. It must touch the bottom to be able to push up. Okay, I'm going to stop there.